Good afternoon and welcome back to Metal Forming Magazine's second annual hot stamping experience. This year presented as a series of educational and informative webinars and still featuring though a plant tour where you're going to get to see hot stamping in action, albeit as a virtual plant tour this year, unfortunately. But it's going to be great. It occurs later this afternoon, so hopefully you'll be able to stick around and join us for the plant tour. So my name is Brad Coogan. I'm the editorial director at Metal Forming Magazine and at the Precision Metal Forming Association, and I am very pleased to serve as your moderator today, which is part 3 of our webinar series, which we started last week. So hopefully you were able to join us for those sessions last week, but just as a reminder, they were recorded as this session is also being recorded, and all of the webinar recordings will be archived on our website. We'll send you a link to view them and share them later this week once we get them up on the website. So look for that email from us. Also, I need to remind everybody that participants in this meeting are in listen-only mode. So that means that the speaker and other listeners will not be able to hear any audio from your site during the program. However, you can communicate with us throughout the program by submitting your questions and comments using the question box, which is located in the right-hand control panel on your GoToMeeting screen. So you'll simply type your question to an organizer selected from the drop-down menu. And then you'll use that same question panel to ask questions of our speakers at the end of each presentation. Lastly, before we get started with the presentations, I want to take a moment to thank our event sponsors, Shei, Fagor, and TJ Snow. Without their support, we would not be able to bring events like this one to you. So much thanks to them. And to kick things off this afternoon, our main event sponsor, Shei, has provided a short video which features some really excellent clips of the hot stamping process in action. So enjoy this very short video, and then we'll be back to start today's presentations. Okay. Again, thanks to Shei for providing that video, and thanks to all of our sponsors. So now it's time to begin today's webinar. We begin with a talk titled Laser Cutting of Hot Stamped Steel, and our presenter is Dan Polto. Dan is a sales engineer responsible for sales and support of multi-axis laser cells with Prima Power North America. He's got 27 years of industry experience in lasers as well as in welding and EDM technology, working with companies in a variety of industries, including agriculture, aerospace, military, appliance, and the construction market. So please welcome Dan Polto.
Well, just like Brad said, my name's Dan Polto, and I am the sales engineer, one of a few, but for Prima Power. And I specialize only in the 3D laser systems group. Today, I wanted to talk to you about the history of the 3D laser cutting and some of our current components and activities that, when utilized, create a higher efficiency in the machine tool and shorter cycle times within the hot stamp line. Finally, I also wanted to touch on where I think we're going in the very near future. So, talking a little bit about ancient history, and I do mean ancient, but Prima Power's first step into the laser market was the introduction of the ZEC, 1979. The machine was set up not only to laser cut, but also to weld. The 1.5 kilowatt CO2 laser was supplied to General Motors in Linden, New Jersey. This particular location was cutting floor pans and welding panels as well. So let's jump up a little bit and start with YAG cutting technology. The YAG lasers of the day were a continuous wave fiber delivered beam. This gave the automotive industry the ability to integrate a robot for applications such as hydroform tubes and simple hot stamp parts. The marriage of the YAG laser source and the robot would be the beginning of the modern industrial laser cutting cell. Here's a few notable advantages of the system. They were easily integrated and maintained, and there was no shortage of skilled programmers utilizing RML or robotic machine language programming. The entire setup was modular, and the robot stood up on a base, and a protective cabin was erected around the robot, and whatever fixturing was needed. There were some disadvantages, though. They were less accurate than a 5-axis CNC, and they did have slower processing speeds. Generally speaking, they had a smaller work envelope as well. There was no means of automatic focus control, and finally, the consumables such as flash lamps were very expensive. In the 90s, we saw the introduction to the true laser cutting machine tool. Generally speaking, it was used in niche markets, prototyping, and low volume cutting applications before taking its place in the hot stamp line as we know it today. It was a ball screw driven machine with high dynamic axes that yielded higher trajectory speeds versus the robot counterparts. The dedicated machine tools of the time could attain position and repeatability accuracy of 0.03 millimeters regularly. They're equipped with a CO2 resonator, giving them anywhere between 2 and 5 kilowatts of cutting power. Later advancements saw the introduction of automated focus control and the solid state laser by IPG and the disc laser from Trumpf. Convergent later came into the market a few years later. Machines of this time period were cutting around 8 meters a minute in comparison to today's machines cutting upwards of 20 meters a minute. So we discussed a little bit about the machine tool history. Now let's talk a little bit about the hot stamp early history. In the early 70s, we first saw the introduction of hot stamped steel being utilized by the Plannja company. They're a division of the Swedish Steel Company. The original motivation for using the technology was for the lengthening of the lifespan of farming implements, such as farming implements and saw and lawnmower blades. 1982, we saw the adoption of the technology in the European automotive market with Saab, Rover, and Jaguar. These companies introduced the shift towards lightweight components for fuel efficiency and a focus on safety as well. All through the 90s, the hot stamp technology was adopted and expanded through the European and US manufacturers such as Ford and GM, Volkswagen, Porsche, Volvo, Daimler, Bentley, Land Rover, and BMW. According to some forecasters, part usage was estimated to be about 3 million parts in the mid-80s, jumping to 8 million in the year 2000, and beyond 2016, parts usage jumped past 600 million parts per year. Some of the parts we're talking about are door beams, front walls, front bumpers, rear bumpers, obviously A and B pillars and rocker panels and reinforcements, as well as roof bolts. I'm going to kind of gloss over the process of hot stamping as other people on the panel will talk about it, and you've seen it in video as well. But we'll just kind of gloss over it. So the blanks on the top there are cut from coil or sheet, robotically fed into a high temperature oven where the blank will reach about a temperature of 900 degrees Celsius. It's a 4 to 10 minute process depending on the blank. After reaching temperature, the red hot blank is transferred robotically to a forming die. The blanks are stamped and cooled under pressure for approximately 20 seconds. During this time, the part is quenched in the closed die. The formed part now leaves the press with very high mechanical properties. So up to about the 2000s, we've been able to keep up with both production and laser cutting speeds with YAG or CO2 lasers. In the early 2000s, we saw the need to process parts faster to keep up with demand. With the introduction of the solid-state fiber lasers from both IPG, Convergent Photonics, and Trump's disc laser, the laser source now cuts faster than the machine tool can keep up. Machine tool builders had the problem that the machine could no longer keep up with cutting speeds of the laser. The market now saw the introduction of what we now call the modern fiber delivered machine tool. The newest introduction of machine tools had the following attributes: a rigid base, a welded tubular base and framework in the case of the Trump machines, or a granite base in the case of the Prima machines. Axis motion was either ball screw, or in the case of Trump machines, or linear drives in the case of the Primas. To overcome the abrasive nature of the dust particles, improved sealing of all axes and bellows and the head seals had to be done. We found that the fine grit would work its way into the machine tool, causing premature failure of the drive components. So stronger dust and fume collection was introduced to keep up with the particulate load. As the shop floor became more congested with the stamping line and increased dunnage boxes, the machine tool builders decreased the footprint in relation to older style machines. In some instances, as much as 30% savings was introduced onto the floor. Turntable indexing speed was now faster, from 4 to 5 seconds in older style machines to 2.5 seconds. And dedicated hard tooling was also controlled by the machine HMI to actuate clamps and secondary programs for part rotation when the application actually demanded of it. So looking at CAM software through the lens of cycle time reduction, collision avoidance, and overall part processing had been identified as a best practice in recent times. A good high-end CAM software is a digital tool. It takes the native file and creates, in conjunction with a programmer, a collision-free post to the laser. Offline programming, or OLP, totally removes the time-consuming need to hand teach the equipment the program. Unproductive use of the machine is done away with, and we're no longer required to teach a machine with a scribe line and projected light. Programmers can reliably create cutting paths for cutting hot stamp parts regardless of the geometry. Collisions with other part profiles, clamping devices, or machine components can be removed altogether. In short, offline programming lets you avoid tedious and unproductive uses of the machine. Many good OLP providers have long-standing relationships with machine tool builders, allowing them to import graphical representations of the actual machine into the software, aiding in the overall programming performance. This three-way relationship is created: machine tool builder, OLP provider, and the customer. Training and after support are generally stronger between the software providers and the machine tool builders, resulting shared technology to the user. So before we even get into part programming, it's often necessary to find the best orientation for the part in the fixture. This will allow the programmer to maximize single plane processing and alleviate any collisions between the head and fixture clamps. On the top slide, you can see the example of a possible head collision by a poorly placed clamp. The head would need to retract too far out of focus to properly even cut the part. While in the offline stage of programming, the change is very simple for the designer to make. They'll get positive feedback from the CAD model that the fixture is going to be in the best possible configuration the first time. This virtually eliminates the need to add expensive modifications to the part, to the as-built production fixture before mounting to the machine. Another important step is the concept of single plane processing. And by this, I mean grouping the profiles to be cut in X and Y axes while minimizing any head rotations. Head rotation around the Z axis on the trump laser is represented as a C axis, while on the Prima, we call it A. The tilting head axis is represented in both trump and Prima as B axis. The reason our goal is to minimize the head rotation is simple. Rotating the head in machine movement is a slower movement in relation to linear movements in X, Y, and Z. So we like to identify the group profiles where possible before jumping to another plane. We'd also like to look for opportunities to skim the surface. And by that, I mean having the opportunity to not retract the head out of the path to get to other profiles. By capitalizing on the rapid traversability of the machine, we can cut a few cumulative seconds in the overall part cut time. In the instance that we have an isolated geometry, we may even want to just possibly interrupt the trim cut and hop to that particular profile and then resume the trim cut. In this slide, you can see the cut profile. It has an impression where the initial thought would be to rotate the head to keep it normal to surface. In this case, the impression is only 3 millimeters deep. If we do not rotate the head and lock it, we can pick up some time. We leave focus slightly, but there's really no appreciable degradation to edge quality. And looking at the left slide here, we program the head normal to the part by rotating the head. There's actually two rotations here if you're actually looking at it. One moving from the top left down the profile, and the second being from the downward arc to the straight cut profile, moving to the right. In this instance, on the right side, we can stretch the rotation. And by this, I mean slightly coming out of normal by about 15 degrees. And by stretching the rotation of the head over distance, we can gain some process speed as well. All offline programming, or OLP, creates posts. They're point-to-point or linear or circular interpretations. By using pre-programmed software functions, we can smooth out and remove excess points. Using a smooth curve algorithm, for example, along with removing excess straight line points, there were 659 points all along the perimeter of this particular part. Using some of the pre-canned algorithms provided in the software package, it removed 403 points, each point being a data block that needs to be processed by the control. The smoothing out function allows for a smoother movement of the machine, alleviating the potential for slowing down of the cuts. Sometimes even more data points can be removed manually to gain seconds here or there. The best practice, goal, or part optimization would be to accumulate all the saved seconds to increase cutting production numbers over the shift and the entire day's output. Well, this next portion of software is not really related to cutting or part programming, but it's a component to software that's starting to take root and be increasingly utilized both on the shop floor and in office communications. Performance data can be monitored at the cell level or in the office for cycle time, number of parts cut, time to cut next part, consumption of gas, and electricity. Machine time reports can show in real time laser output in parts, runtime, and idle time. Machine failure, idle times are specified in screen reporting. No idle time remains unexplained. Performance reporting reports all machine time. Processing time is recorded when the machine is actively running. Idle time is defined as the time when the machine is ready for cutting. Faults are automatically recorded in time by the machine status. Idle times can be defined by the user to describe the reason why the machine was idle. For example, lunch or coffee break, tooling changes, stacking area clearance, etc. Fault errors. Messages are recorded to identify what alarms occurred during this time. Alarm history data is available as a graphical report. It shows when the alarm occurred and for how long it lasted, which program was active at that point in time, and which tool and material was used when the alarm occurred. With this information, the reason why the alarm occurred can be found. The alarm history can be reviewed to help maintenance departments be proactive in reacting to reoccurring alarms that may happen. So productivity, efficiency, and machine effectiveness are a goal that's often shared across every manufacturing company. One of the best metrics used to drive improvement in manufacturing is OEE, or overall equipment effectiveness. It's my opinion that you cannot have any equipment effectiveness without paying attention to preventative maintenance. Here we're going to break down some of the major parts of preventative maintenance as a contributing factor to the laser cell reliability within a hot stamping plant. So all 3D lasers can be broken down into the following groups, and these are large groups: the laser source, the optical chain, the cooling system, pneumatic system, motion system, focusing head, and fixture maintenance. The fiber laser source does not require any preventative maintenance. Each generator is composed of independent modules connected to a combiner through fiber optics. There's no free space propagation and no mirrors or lenses to be adjusted or cleaned. In the case of module failure, it's possible to continue cutting with reduced power because of part redundancy until the module is replaced. In the case of the trunk disc laser, their configuration is a little different, where the beam is generated and then bounced by way of mirrors, and then it's combined to the fiber. This process is different. For the most part, it's sealed up from the environment and not needing any preventative maintenance. The optical chain consists of the delivery fiber marked as A, that links the laser source to the collimator, marked as E. Through the cable tracks B and C and D from the collimator, the laser beam propagates toward the bending mirrors, all the way down at G. Focusing lens and protection glasses is pretty much the same setup in every current day fiber on the market. From the laser generator to the collimator, the fiber cable is connected and protected and set away from all the manufacturing processes. There's no real maintenance activities required there at all. Any maintenance that's done is done at the head, and they're as follows: lens centering, lens and glass and mirror checking, and a thorough cleaning, and finally, lens, glass, and mirror replacement on an as-needed basis. The cooling system, the chiller unit chills the laser source and the optics. In the case of the Prima machines, it also chills the linear motors. General maintenance activities to keep the system running at peak efficiency would include checking and topping off the water reservoir, replacing of the water altogether at recommended yearly intervals, periodic filter checks, and filter cleaning and/or replacement. With regard to the pneumatic system, the laser machine will be connected to a compressed air line if the laser is set up to cut with compressed air. The air treatment unit with an air dryer and different array of filters provides dry and clean air for the cutting process, actuating the lubrication systems as well as actuating clamps and cylinders throughout the machine and fixtures. As a general rule of thumb, dirty, oily air will always find its way to the optics in any other place it doesn't need to be and accelerate downtime. Preventative maintenance activities around the pneumatic system are generally centered around filter replacement, such as replacing the filter particle canister, activated carbon filter changeouts, condensation drain checks, and moist air outlet cleaning. The laser machine is equipped with linear motors on X and Y axes in the case of the Prima machines, whereas the Trumpf lasers utilize ball screws. Rack and pinion on the Z axes are present on both manufacturers. Maintenance activities are centered around the following areas here: linear guide lubrication, checking the automatic lubrication reservoir, replacing sliding blocks on major axes, X, Y, and that would be Z as well, checking the Z-axis gearbox, rack and pinion, optical scale cleaning, bellow checking, cleaning, and replacement if needed. In the case of the Trumpf machines, a check of all the ball screws for lack of lubrication while looking for possible clogged lubrication lines is there also. Should also be noted, we need to check and inspect wipers and seals on all those ball screws as well. So with regards to the focusing head, there's been a good bit of engineering done here to seal and protect the inner workings of the head from both manufacturers. Most of these activities are centered around the head and have now been either automated by the control or relegated to general housekeeping. So the head and the tip cleaning should be done every other shift. A tool tip check and replacement is needed. Checking focus position, and activities such as beam alignment, head offsets, and sensor checks are often automated as well. Fixture maintenance is just as important to the cutting process, but it's not often paid much attention to until there's several parts are repeatedly cut bad or a noticeable shift in geometries are noticed over time that can't be explained by the program post. I broke these checks down to 3 simple groups: 1 check per shift, 1 check per day, 1 check per week. 1 check per shift could include reference pins, location supports, and powered clamps, including indexing cylinders and magnets. 1 check per day Might include copper and steel shielding for damage and replacement as needed. And a weekly check might include brackets, hoses, electronic cables, and plugs. And when you remove the tool, maybe even checking the fixture surfaces for dirt and debris. So we've kind of talked about the machine tool and maintenance programming. Now I want to kind of jump into the future a little bit of what's coming down the road. Can't really speak for my competitors' future developmental activities, but at Prima, we're currently starting to deliver integrated check systems and integrations where fundamentally change the downstream look and overall function of the cell. We're always going to provide standalone cutting cells, but in the case of the hot stamp line integration, Prima has shifted to an evolutionary step to integrate robotic loading and to become fully part of the line. Current tier ones and small run hot stamp companies are requesting an external poke-yoke device that can be integrated into the cut cycle to check parts. In the case of the integrated poke-yoke device, the robot or the operator places the part on the fixture, and the machine will get a simple pass-fail signal, allowing the machine to cut the next part. If the part fails, the operator or the robot will drop the part in the scrap bin, and the cut cycle is started over again. The machine reports the scrap event to the performance reporting software if it's used. Vision systems as well. An integrated vision system inside the machine compares the CAD model to the cut part. All the holes are verified, that the scrap dropped fully, the hole diameter as well as overall part geometries are also inspected. The vision system is programmable to the shape of the part. Doing this process inline is saving approximately 4 seconds per hole compared to the old hole scrap check done with the nozzle. All the profiles can be checked in a few seconds before the part even leaves the cutting cabin. Later, we'll talk about robotic integration in the line in the next couple slides. The main drivers for robotic integrations are the parts can't be handled by a single operator due to the overall size or weight, or the robot is used to avoid ergonomic issues. The robot can be introduced into the cell where there is no need. The robot can be introduced into the cell when there is a need to reduce headcount of the staff who just handles parts. The robot can be introduced when the cycle times are too short due to developed trim, or an operator just generally can't keep up with the loading and unloading of smaller parts. Geographic areas with higher labor costs can also benefit from a robotic integration as well. The left picture shows a laser system equipped with one robot to load and unload parts from a supplied rack. There are no operators until the part change or maintenance is required. And this is the lowest cost per part solution when one cell is saturated with one part. The right side, the flexible hybrid system allows for an automated robot load and unload of the part. The robot travels up and down the work area on the trolley track, picking up parts for the cut cycle. Upon completing the cut cycle, it places them back in supplied racks. This system allows also for manual loading and unloading of planned short-run parts where a robot is not required. The operator has an easy access to change out fixtures as well. Now, this video that's embedded here is a test run of the left photo that you just saw. These two systems shown here take full advantage of robotic integration, part inspection, and a part buffering system to feed a downstream line. The lasers have a simpler enclosure with no turntable at all. There's a guillotine-style door that rolls up to allow the robot to directly place the part on the fixture in the cutting envelope. Upon completion of the cycle, the part is taken to Poka-Yoke devices for inspection. Critical and non-critical points are inspected, pass-fail signal is generated, and it's placed in the buffer for downline processes. If the part is considered scrap, it's placed in the correct dunnage bin for future removal. Both systems here were designed for fork truck or AGV introduction of unprocessed part racks. So up until now, we've seen laser cells working as single cells or multiples. Currently, we're integrating and changing the form of the laser to be introduced as a member of the manufacturer line and not a station off to the side. The left picture shows how hot stamp parts are being robotically loaded and unloaded from the cutting station. As the parts come off the PHS line, they are conveyed directly to the laser. The robot, with its end effector, loads the part on the fixture for cutting. After cutting the part is presented, it's presented to one of the two rectangular inspection stations at the top of the slide. At the top of the slide. Upon receipt of the pass or fail signal, the robot will then place the part back on the conveyor for downline processing and final assembly. The entire line is integrated into a much larger line. And in this slide, the protection cabin is not shown, but it is that large gray box encompassing it. Again, the picture on the right, the protection cabin is not shown at all. But in this integration, to make the best use of floor space, the machine tool was actually rotated, and the part is actually introduced to the cut envelope by the way of a guillotine door that you can see from the side. The turntable, again, is totally done away with. The robot simply reaches in, directly places the part on the fixture, and again, upon completion of the cut cycle, the part goes to vision inspection and then downline for future processing. So that's it for my portion of this event. I want to thank you guys for your time and your attention, and feel free to reach out anytime if you have any other questions.
Thank you, Dan. Thank you very much. We do have a little bit of time for some questions, so go ahead and use that question panel down there on the right-hand side of your GoTo screen. First question, Dan: is it better to laser cut uncoated hot stamping materials like 22Mn boron, or uncoated before or after shot or sandblasting, and why?
Oh boy, I'm not sure how to answer that one.
Okay.
Well, I'll tell you what. If you want to email that to me, I'll get back to you with an answer on that one.
Okay, Thomas, why don't you go ahead and email Dan your specific question, and
I'll get you. I'll get a good answer for you on that one.
Good.
That one
Okay, cool. So the next question has to do with speed and how to increase cutting speed, but she didn't tell me the type of material or the gauge, which I know has something to do with how fast you're going to cut it. But she says, how long does it take to laser cut a 10 millimeter hole, a circular hole, and a hex hole? And then what are some general steps, I guess, to take to increase cutting speed? So I don't know if you want to maybe offer an example of some process parameters. How typically are people cutting, the most common gauges of steel?
I'll say for both Trumpf and Prima machines, holes are only seconds. Hexes are a little different. I mean, because we have a beginning end to an angle there, but we're only talking seconds.
Okay.
Uh, Generally, if there is no, uh, I'll call it a slug drop or a slug check. Some people call them coins. You're only dealing with seconds
Mm-hmm.
on a cut.
Mm-hmm.
Um, that the I'll say the old style or the what's currently done often is using the head as a scrap check. That takes a second. Um, we're only talking a second, 3 seconds a hole, things like that.
Okay. 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 Any kind of common advice that you can offer your customers or the folks that are on the webinar today for increasing cutting speed versus what they might be doing today? Is it
Well,
parameter related
gas.
or?
It could be it could always be a function of gas, gas pressure,
Right.
power as well. Oftentimes you're not cutting at full power,
Mm-hmm.
but and many times we revert to the old chip making. It's always a function of speed and feed, but with the laser, it's also gas and power.
Okay. In terms of laser power, are we going to continue to see increases in power for these 3D systems like we're seeing in the flatbed lasers, the 3D lasers?
Yeah, I think that's a natural progression. Right now, for hot stamping, and everything's light. What I'll generally call light gauge.
Mm-hmm.
The 3 and the 4 kilowatt is pretty much the market. Keep in mind that anytime you go beyond that, we've got to start fooling around with the optics, because generally the more power you're shoving through those lenses, the faster they're going to degrade. So we would always have to kind of, if you want to say beef up the head, beef up the optics. I think it's a natural progression. When that happens is they don't tell the sales guys, but it's being done. It's being done right
Yeah.
now. To be truthful, it's being done and rolled out to customers on a one-off. Generally not in a hot stamp right now.
Okay.
Hot stamping situation.
Your discussion of maintenance, preventive maintenance.
Mm-hmm.
What where does making sure you're supplying clean air to the process? How does that fit into improving quality and or productivity?
Okay. Well, clean air starts at your compressor. Well, actually, right after your compressor. I'm sure my competitors at Trump, or actually any of the laser, manufacturers, that haven't really jumped into a fiber laser market yet. But I think everyone would agree that clean, dry air is the best way to keep this laser system up and running. Oil will always find its way. Dirt will always find its way to the optic. I've seen it on old machines, and I've seen it on the newest machines. Any kind of dirt in the line. So if there's an air dryer and some type of a cleaner in line before the laser, that catches everything. What you saw on the back of those machines, it's not entirely true to call it a last ditch effort to keep everything clean, but that's what I tell everybody. If it's not clean before there, all those filters are going to cake up hard and fast.
Okay. Good advice. Okay. I don't know that we have any other questions for Dan. So Dan, thank you very much. We appreciate your time and your very informative presentation. Some really good tips in there, I think, for the folks that are using 5-axis lasers, and some good advice for people that are looking to get into the process for the first time. So thanks again, Dan.
Yeah.
So we'll move on now. Our next presentation then addresses resistance welding of hot stamp steels, and our speakers are all with TJ Snow Company, as you see here. Joining us are Tom Snow, who's the president of the company. Also, Tom is a certified welding technician. Welding engineer Jeff Morgan, and then Ray Michelina, who's also a certified welding technician and conducts several seminars a year for TJ Snow as well. So please welcome Tom, Jeff, and Ray.
Well, thank you. Appreciate for the introduction there, Brad. Hope everybody is fine this afternoon. We're going to lead off with just talking about hot stamp steel. It was a excellent video you had there at the beginning, Brad, of showing what hot stamp steel is and how it's performed. And Dan, for explaining the process a little bit, definitely was beneficial. But we're going to talk about hot stamp steel when it comes to the projection welded fasteners. That's what we're going to focus on just this afternoon. You can do regular spot welds on the hot stamp material, but we're just going to focus on the projection welded fasteners because that seems like what's given most people the problem. You can see here on the screen where we show several examples of some issues that we commonly see with people that are doing especially weld nuts to the hot stamp material. So what is that hot stamp material? Well, we heard a good explanation of how it's made up at the top. And so because it's created into this hardened material, that's what creates a problem for us in the resistance welding process. The other thing that happens during this process, it puts a surface oxide layer on the material. That aluminum silicone's a very resistive coating, and it's also very inconsistent. Anytime that we have any coating on any type of material that we're going to weld, it's considered a contaminant. And so for us, that really does make it difficult for us to weld in resistance welding. So let's just talk about a few basic things with resistance welding. First of all, it's a science. It's not black magic. It's understood and it can be manipulated. And there's some ingredients that we're going to be talking about that's common to all types of resistance welding. And we're talking about projection welding today. And so there's going to be another ingredient that we're going to talk about. But we have force, current, and time. Each one of those ingredients makes up the recipe for a resistance weld. And the same thing on our projection weld. We must apply a certain amount of force, pass a certain amount of current for a certain amount of time in order to create that molten nugget. And basically that's what we're doing with a projection. We are taking that projection and that's our spot weld. So if we have 4 projections on a nut, we're doing 4 spot welds at one time. The one thing about doing a projection weld is that we need a very great follow-up system because we're actually using the projection as the welding points. And so those welding points, when they start to collapse, we must continue the correct force because that force is actually creating that resistance. Then we're using resistance welding, but force creates a resistance, resistance creates a heat. And so we must have that follow-up with projection welding. And you can see here in the video on the welder that we're using on the left and a close-up on the right, we actually use some way to give us a constant force. Using a pneumatic system, we have air compressibility. And so that doesn't give us a constant force. So that we use a welder that has a ram. You can see it's a guided ram with the cover taken off. We've taken the cover off just for to be able to show you what's inside. But there's bearings that keeps that ram perfectly straight. We don't want any movement whatsoever, any deflection in the system. Any deflection in the system is going to create problems for us when we're doing a weld, a projection weld. And so we have a spring that we preload. The ram pushes down on that spring so that we have a amount of energy available as soon as those projections start to collapse. They're using airbags a lot of the times now, like the small ones that are on the back of a semi-tractor cab, that they are using airbags on a lot of the welders for the same thing. But in projection welding, having that follow-up is one of the crucial points that we're looking at. But there's some principal challenges that we have with resistant projection welding on hot stamp material. First of all, there's a thing called the shift of a failure mode, that we go from the fracture in the sheet-based material to failure in the weld joint or fastener projection material. This is one of the hardest things for people to get used to. Everybody with projection welding or resistance welding, in fact, is always used to pulling base material, pulling a nugget out of base material. Well, with the hot stamp material, that's hard to do. Number one, because usually the base metal that we're dealing with, the ultra high strength steel, harder than actually the projection that we're dealing with. And so that difficult to develop a weld bond stronger than the ultra high strength steel. So the weld usually fractures when we're doing a projection weld. May not be an issue with the strength of the weld, just because we're using a weaker link, a weaker material on the projection nut itself. So if the weld fails but the base material doesn't, material's high strength, or was it a cold weld? That's what we have to determine. We have to look at what's going on with that weld. Is it a strong weld? Can we pull metal maybe in a thinner sheet of the hot stamp steel? We can, but that's not what's normally going to happen, because the weakest link fails first, and that may be the fastener that we're dealing with, because they're not made of ultra high strength steel. So the pulled metal and destruct test is no longer feasible for certain applications. So when you're doing your testing, you're going to have a robust test that's going to test the strength of the fastener and how it was welded, instead of what normally we would do as a push out or a torque test of, let's say, the nut. That it's going to have to be something that determines how much strength is actually in the part. So with our hot stamp steels, we've already seen how it's an in-house process, but that really varies from manufacturer to manufacturer. And so that even affects the material hardness variations. For us in the resistance welding world, where we depend upon the material being a certain weldability, when we have variations in the strength and variations in that coating that we talked about earlier, that's really difficult for us in the resistance welding world. That surface oxide coating variations exist in the industry and even across the part in terms of contact resistance. Again, this is resistance welding. We have to have a certain amount of resistance, because that's what creates the heat when we pass the electrical current through there. So if we have 4 projections on a nut or on a bracket, let's say, and we have a variation in the resistance in the coating on the material from a projection to projection, that makes a difference in the heat that's spread between those projections. There's only the resistance of each projection, which determines the heat that's going to be at that projection. So hard, less conductive aluminum oxide thickness may vary, which just adds another problem. And a few micrometers variation can cause previously approved setups to fail destructive test. So no matter what you have set, that just a variation in that coating can really cause your test to fail. And so there's really no visual way to tell the difference in those parts. So we have Jeff Morgan here, and we have Tom, that we're going to just go through a little bit of discussion on these projections. I've got some questions I'm going to ask these two experts, and we're going to see if we can't answer some questions for you before you even ask them yourself. So we've got some pictures here of some nuts that's a little bit different than what we would normally expect on projections. And Jeff, if you would kind of lead us in and let us tell us about what we're looking at here.
Well, if you'll look at what you have on the screen ahead in front of you now, you'll see the bottom center picture is actually a hot stamp material. And one of the things that I guess companies and sometimes welding engineers miss is doing their homework. And a lot of the things Ray discussed a few minutes ago, for example, studying the projection and what strength is going to be needed by the end user. A lot of times we're prone to go with the cheapest fastener possible. You all are familiar with the square nuts that have, we call them lunar landers sometimes because they have small projections on them. Those projections are typically not parallel or not level, so the fastener, each of the projections has different amounts of force on it, so it will react differently in the welding process. So it's better to choose a nut with more stable projections so that they can do their job. Because remember, in projection welding, the projection is what's doing the work of the electrode, typically in spot welding. So we want to focus the energy, and we want to focus it continuously throughout the weld. If you'll look at the photo in the lower right-hand corner, you'll see that those are banana-shaped projections. Those are very, very good for the process because they're very stable. They're able to, if you will, help break through the coating, and we'll talk a little bit more about that in a minute. The ring projection on the upper right is also a very, very good projection design for welding on hot stamp materials. One of the major reasons is the lower level of expulsion. With ring projections, we get very, very little expulsion as compared to a single or a segmented projection. So that's a benefit. It's a very, very important that the fasteners that are selected are actually reviewed prior to the assembly process to make sure that the projections are always the same height. So it's important that your fastener provider go through a stringent quality control process. Go ahead.
Jeff, one of the things that I noticed on the ones that you pointed out on the right-hand side there, seems like the projections are quite a ways away from where the threads are compared to the nut over on the left bottom. Does that make a difference?
Yeah, that's really a good question, Ray. It helps improve the let's use the word threadability, the stabilization of the threads in the fastener. We want to keep that weld as far away from the threads as possible, because any of you who have these parts in process right now that know that a little BB of expulsion in can cause you a lot of heartache in the assembly process. So it's very, very important to keep that away. And the farther that the projection is away from the center, of course, we'll need more energy to do it, but it keeps the expulsion away from the threads, which is really, really crucial.
Okay, very good. I appreciate that. Well, I'll tell you what, we've got some questions here that we're going to go through, and I'm going to go ahead and bring the questions up, and we're just going to have a discussion here. And so for you that are in the audience, these may answer some of your questions that you have already. So if we have a weld projection fastener now, what is going to be the different welding? What is going to be the difference welding projection welded fasteners to hot stamp steels? If we're already doing this process, Jeff, and we get this job to do this on hot stamp steels, what are some of the big differences we're going to look at?
Well, probably the most important thing is something that Ray mentioned a little bit ago, was follow-up and the robustness of the welding machine. It's extremely critical that the upper and lower platen remain parallel. We've seen many applications through the years where the electrodes are offset, so we get a little bit of deflection. And any deflection at all in the process, not only is it bad for hot stamp steels, but it's bad for any projection operation. So it's very, very important that the machine be very stable. Other things that could be added to that are emphasize the fast follow-up. Basically, that, as Ray described earlier, that's a stored energy process. So we're storing the energy in that spring. And if you think about the projection, as the projection goes plastic, it's going to start to collapse. And as it collapses, the ram has to follow up behind it to keep the welding force stable throughout the entire process. So that's really, really important in this process. A few of the other things are good water cooling, just everything you would normally do to keep the process stable.
Very good. All right, Jeff, is there an easy way to visually tell if I'm welding hot stamped steel?
Typically, the gray oxide is the easiest way to tell. Most other materials are going to be shiny and have a nice metallic look. The hot stamp materials are grayish, or I've seen them purple, gray, green, many other colors, but it's sort of an oxide on the surface of the material. So that tells you right away that you're getting a part that is hot stamped.
Okay, good. Well, if there's such difficulty with projections in the nuts being so soft or the brackets, why don't we just put the projections in the hot stamp material?
Well, it probably would be a good idea, except it would be difficult to maintain. Putting the projections in the fastener is generally the accepted way of doing it. Plus, we have the issue with inertia of the fastener. We don't want to be moving that heavy part towards the fastener. We want the light fastener to be moving towards the part as the projections do their job.
Okay. And in the picture that we were showing there, that there was a full ring style projection. Are those typically used for welding on hot stamp material?
They are on many applications where the fastener has to be water and or gas tight. For example, on an underbody portion on a car where you might get exhaust leaks that would seep into the passenger compartment. Typically, the trend is going to more and more ring style projections. And as I mentioned earlier, they are very, very easy to weld, provided the machine is sized properly.
Okay, and machine sized properly. Now, you keep talking about that we need a fairly robust machine and doing projections, that we don't want to have any deflection. And the power for the machine, are you also saying that we need a machine that is going to be rather high powered as far as output?
Well, as we all know, with projection welding, it's important to keep the weld time as low as possible and let the current do the job. So remember, the formula is I squared RT. So as long as we have the same amount of energy, we're going to make a weld. But how well can that weld be maintained throughout the day or throughout the shift's process? So it's very, very important that we maintain the lowest weld time as possible. That will do many things for us. It will reduce the power bill, and everybody likes that idea. It will increase the lifetime of the electrodes, and it will help stabilize the process.
Well, good. And you had brought up a little bit ago about the expulsion getting into the threads causing problems. Mm-hmm. Can we just use piloted nuts to get away from that issue?
Well, it will help. I personally, this is a personal opinion, I don't like piloted nuts as well as the conventional nut, because sometimes the pilot will land on the edge of the flange and cause a problem. But in general, it might help protect the threads from expulsion.
Okay, good. Well, in today's world, it seems like we're getting so many of the powdered metal projection fasteners that are out in the industry. How well do they work with the hot stamp steels?
Well, as of right now, we don't have a lot of experience welding powdered metal with hot stamped. We do have a tremendous amount of experience welding hot stamped to some stainless products and also to some mild steel, and it works quite well. We also find that it works much better with capacitor discharge than it does with MFDC or AC. So that brings some other advantages to the table. We get longer longer electrode life, we get lower power consumption, and we get a much more stable process with the powdered material. The other thing with powdered material is always important to remember is who are you buying your powdered metal fastener from? How are they quenching it? Are they letting it air cool, or are they quenching it in oils? The material by its nature, if it's quenched in oil, has a tendency to absorb the oil and will actually then bake out during the welding process, causing unstable or undesirable conditions.
Well, you had mentioned using electrodes and some of the different components of projection welding that we're able to use for welding this. Welding this hot stamped steel, can we use the same electrode or the same consumables for doing this type of weld?
I personally think class 2 is probably the best. It's the cheapest material. It seems to work relatively well. A lot of folks tend to like electrodes with either an alkanite face or some other coating on the face of the electrode. That does extend electrode life in some instances. If your process is under control, though, it should not be necessary. So I don't see a real need to increase cost of electrodes unless, as you go through your productionizing of your equipment, that you find that it does decrease downtime and increase electrode life, then of course you should use it.
Okay, very good. All right, now I know in regular projection welding or regular spot welding that if there's a coating on there that we can usually try to get rid of that coating before we weld. Is the oxide coating on the hot stamped steels, does it react much like the galvanized coating where we can get rid of it before we go to weld, or is that just something that's always there?
Yeah, we can get rid of it. One of the advantages to this oxide coating is it's removable by a pre-pulse. So what we found is that a 10,000 amp approximately at about 4 millisecond pre-pulse will allow the projection to, if you will, eat through the oxide coating. And we are able, by doing that, by using a pre-pulse, to go from a change in push-out values from, let's say, from 1,000 pounds of push-out up to 2,500 pounds of push-out. That much range. If we remove the oxide coating with a pre-pulse, we find that that range settles down at about 200 pounds of different push-out. So it's a very, very important thing to do if you have the capability with your welding machine. Now, one of the things you have to consider is, are you using AC, MFDC, or potentially capacitor discharge? Many people that are welding hot stamp fasteners today have been sold on using capacitor discharge. Now, Ray has a slide up now. If you look at the right-hand slide, you'll see what the projection is subjected to. You can see the capacitor discharge waveform. You can see the MFDC waveform next, and then you can see the standard AC waveform. Now note that the capacitor discharge waveform gets to the business of welding much faster. Now just consider these tiny little projections. Those little projections are going to be subjected to a lot of heat. So look at how fast each of the processes gets to the maximum heat. So that's one of the reasons capacitor discharge is much better for projection welding on hot stamp, is because we get to the business end of the deal much faster. So the projection is allowed to do its job. If we use MFDC or AC, we melt the projection somewhat gradually, so it collapses before it's ever allowed to do its job. So it's something to consider. if you're starting a new process where you're using hot stamped and projection welding of fasteners, it's important to consider capacitor discharge as one of your major options. It appears to be, in our experience, the direction that the industry is going today to weld it. You will see on the left-hand slide, this is our own TJ Stowe capacitor discharge process monitoring system. You'll see that it looks at all of the parameters that could affect the weld and also generates a waveform so that the welding engineer can very easily analyze a weld to make sure that it is a stable process. We can also send a signal to your PLC or your robot or whatever is running, or to the operator, that we had a no good weld or an out of process weld, and stop the process so that the part can be removed from the production lot.
Very good. And this that picture that's on the left, that's a real-time picture.
Yes, that is a real-time picture. It shows our latest machine, which is a 3-head CD welder. Just a little sidelight. Our machines are being used to weld all of the fasteners on the body side of the new Ford Bronco. So all of the hot stamp material that's on the body side is all welded with a TJ Stowe capacitor discharge welder.
That picture of the nut, is that one of those that has that sausage style?
That one does, I'm pretty sure. You can't see all the screens on this, but there's this screen, we're able to set up a set of parameters for each fastener geometry, and then the welding engineer can very easily switch back and forth between fasteners to make sure that he can have a record of how to weld it.
Okay, very good. And this is showing real time, so the drawing over on the right-hand side is not just a drawing. This is the fast rise time that we're seeing in the capacitor discharge. That kind of leads into our next question there is, why will the capacitor discharge process provide the best weld? So over the AC and MFDC, why do you say capacitor discharge best?
One major reason is the rise time. The fact that, as I said before, the welder is able to get to the maximum current very, very quickly. And because of that, we can add the pre-pulse, and that's why I mentioned earlier that some equipment is not able to do that. We can add the pre-pulse at the beginning of the weld to remove the oxide and thus stabilize the process. So we're getting very, very good feedback from that process. It works very well. It stabilizes the process. We're able to get very, very stable push out.
Okay.
Now, one thing I wanted to say also about capacitor discharge, it's one of the processes that must have fast follow-up, because the projection collapses and the process takes place so rapidly. For example, an entire capacitor discharge projection weld takes place in about 8 milliseconds. Whereas if you were using MFDC, you might weld it in 100 milliseconds, or if you were welding with AC, maybe 6 to 8 cycles probably. So it's very, very important to consider this process when you're. Now, the disadvantage, and I have to share this with you, the machines are a little bit more expensive, but they will reduce power consumption and they will increase electrode life.
Well, good. If we do decide to go with a CD welder, capacitor discharge welder, is there any special training that we need for our operators?
Not really. The controls are very straightforward. We don't control, and this is something I didn't touch on a minute ago, is that we don't control weld time. Weld time is controlled by the impedance of the secondary circuit. So the weld time is just basically the time it takes to discharge the capacitor bank. So it's very, very easy for operators to learn the process. The one thing that we might mention now is that PM of the machines is crucial to maintaining the machine efficiency. But I can't say that that makes it any different than any other resistance welding machine, in that it's very, very important to maintain the secondary circuit. So if you are resistance welding, you're not doing anything special with a CD welder that you shouldn't be doing with your conventional resistance welding machine.
Now, you had mentioned the capacitor bank. Is this going to make the CD welder larger than my other resistance welders? Is it going to take up bigger footprint?
It does, because you've got a control that's approximately the same size as your conventional MFDC control, but you also have a capacitor bank cabinet that can be about the same size as the control cabinet. So the machine does grow in width slightly.
Well, what about special hookups? Will I need anything special if I want to put my CD welder into my facility?
Well, the really cool thing about it is you can make welds with as little as 60 amps primary power. So where in the past you might have to run, for example, we have customers that had 800 amp power supplies running to their primary power running to their welders. So with this case, you can take a standard CD welder, let's say a 12 kilojoule, and run it on about 60 primary amps, and that particular machine will develop in the neighborhood of 90,000 secondary amps.
Well, is this a machine this CD welder, is it gonna require any special startup procedures? And you'd already mentioned that about this capacitor bank. Is it gonna slow down my process because I'm charging up these capacitors?
No, in the old days, and some of you may remember capacitor discharge from days gone by that took a very, very long time to recharge, and especially to start up in the morning to charge the capacitor bank. In this case, we charge typically less than a second. So about the same time it takes to move the part to the next operation, or to move the part to the next fastener.
Well, good. Now, with all this capacitor bank and this high, the amount of current that we're making these welds with, what about the safety for the CD welder and the CD process?
For the average individual, there's no issue. But if you do have individuals working in your plant that have implant device, for instance, a device to eliminate pain, or potentially a pacemaker, those need to be evaluated by your plant safety department and the individual's physician to make sure that they're robust enough to handle the issues. One thing that I forgot to mention on special hookups, the CD machines for the most part require no cooling water. So it's very, very important to remember that you pay a little bit more for the machine, but you save lots in energy.
Okay, well, very good. And the no cooling water, just because we're welding so quick, we're not building up any heat?
That's correct, because duty cycle is really what generates the heat. So if most CD welders operate at less than like 1% duty cycle. So very, very fast.
And you had brought this up a little bit ago about the maintenance. As far as the maintenance, what can I expect from this CD welder other than different from my other welders?
Just the fact that it's important to annually check the secondary circuit for any, should we say, built up resistance. Check the continuity of each of the components in the secondary circuit to make sure that they were as they were when the machine was built.
Well, if there's with this new process, are my maintenance people and my setup going to need any specialized training for this process?
I would always suggest anybody who's getting a new process to have a familiarization training class for the machine on how to operate it, and also a little bit about the resistance welding process. Because as I'm sure everybody has seen in the past, there's a lot of misunderstanding about how resistance welding actually works. So,
well, the CD process sounds really good, but if I go and purchase this machine, will it ensure the consistency for projection welded fasteners to the hot stamp steels, or are there some other things that are going to be issues?
Well, the stability of your hot stamping process is always crucial. We have seen a lot of variance in part to part, especially in flatness of the area where the fastener is welded. So it's really, as Ray brought up very early in our discussion, that flatness and parallelism of the parts is really crucial. So those are some of the things that potentially could cause a problem. As with any resistance welding process, it is only as good as the parts going into the process. So if the process is not stable, it doesn't matter how good your welding machine is or how advanced it is. If the parts aren't right, we can't compensate for that in most instances.
Well, with this CD process by itself, what are some variables that I need to be aware of as far as, do I need to take a look at what I'm actually doing to see if MFDC or AC works better? How do I make that determination? What are some of the things I need to be aware of?
Well, the important part, as I mentioned when we started, is research, to actually weld samples. I was a welding engineer in a plant for many years, and I would have the process engineers bring me a new part made out of some exotic material and say, here, weld this. And the important thing is to be able to be ahead of the curve and weld parts in a test environment to make sure that what you're getting into. And it may be, as Ray says, that you're a very, very low strength hot stamp material. Maybe you're not up in the 1200 megapascal material, you're down a lot lower. So it may weld just fine with MFDC or AC. But the important thing is to do your homework.
Well, good. If I have any questions or have any issues with my hot stamp steels and projection welded fasteners, how can I get some more help or more information?
You can contact me. My email is right there in front of you, or anyone in the applications department would be able to help you.
Well, good. Appreciate the comments there, Jeff. And back to you, Brad. Do we have any members of the audience that have any questions that they'd like to ask us?
We do, and thanks, fellas, for a great presentation. Really nice conversation on kind of state-of-the-art technology for getting this kind of work done. So appreciate your thoughtful organization of the material. Nicely done. So we do have a few questions. You talked about fasteners, but what about welding press-hardened steel parts to each other? How are you finding success with the resistance welding hot stamp steel parts to each other?
I've been welding hot stamp parts for it's been more than 20 years now since I've received the first parts in the plant. And the real secret to it is fit up. If the parts fit properly, you probably won't have an issue. Now, we can get into a lot of depth here. There's a phenomenon called softening in the heat affected zone. Many people, because of the things Ray talked about, the inspection techniques for the process, where we always look for a nugget. Generally, with hot stamped, you're not going to get a nugget unless you actually soften the area in the heat affected zone. And when you do, then you will get a nugget. But in fact, you have reduced the strength of the material. So it's a whole nother topic for discussion. Maybe we can do that at some other time. But if anybody has any questions about it specifically, just please call me. Great,
thanks. Are process parameters available, online or published somewhere where people can at least get started setting up their machine to weld steel?
No. No.
Okay, that would be too easy, right?
Yeah, that would be way too easy. There's a lot of techniques for welding it. The powers that be at the sheet metal welding conference every year, there's always every couple of years, there's always controversy on what is the best way to weld it. My personal experience is a pre-pulse, as I was describing with the projection welding, is a very, very good way to remove some of that hard oxide on it and to produce a good weld. So typically with it, I've been using a 3-pulse weld, a very, very low initial pulse, and then 2 additional pulses, depending upon how thick the material is.
Interesting. Good. Okay. What can you tell us Jeff and Ray, about the relationship between the oxide coating thickness and maybe how consistent it is even. The relationship to the oxide coating thickness and the weld schedule. Do you have to change weld schedules to adapt for uneven thickness of that oxide layer?
Yeah, let's concentrate for this question, just concentrate on the projection welding. We find that if you do use the pre-pulse, you won't have those issues. If you don't use the pre-pulse, you could potentially have to change welding parameters from run to run, because there appears to be, I'm not a metallurgist, I'm a welding engineer, but there appears to be a lot of difference from run to run on the oxide levels.
And Brad, also that makes a difference, just like we had alluded to earlier about your projections that you're using also. That using a projection that is better suited for the hot stamp material, where it has the strength to hold up to the heat and the force that you're using during the welding process, really makes a difference. So when somebody is wanting to do a projection weld on hot stamp material, the component, the fastener itself, the projection style on that fastener really needs to be a key thing that they focus on. It's got to be resilient enough to withstand the force and the heating, just like Jeff alluded to, that pre-pulse on a normal projection, that would start to flatten the projection. Having one that was substantial enough to handle that is really important.
Great.
Yeah, it's like I was saying, homework is probably the best, the most, I guess, prudent advice I can give.
Sure.
Is do your homework before you try to weld the parts.
Makes good sense. And so that kind of a follow-up question is, so what affects the process the most then, the overall coating thickness or the interdiffusion layer thickness? And that's probably more of a metallurgy question, but
It is to a certain extent, but if you can get through the oxide layer, it does not appear to be an unstable process. Our experience is we've run basically in the last, I'd say 6 months, probably, I would say in the neighborhood of 10,000 that were actually analyzed projection welds on hot stamp material. And with the pre-pulse, we find very, very little difference. So
good. Okay, gentlemen. Well, we're right at the top of the hour. So again, we appreciate your presentation and your time today, and your contact information is up on the screen. So if anybody else has further questions for these guys, feel free to reach out to them. So again, thanks a lot to you guys. So that wraps up the technical presentation part of our webinar series. We are happy to be able to provide a virtual plant tour. We wish we could have done a live plant tour, and perhaps next year we'll get to do that. But we've got a really nice set of 3 videos that Diversified Tooling Group has supplied for us. So I want to thank the team over there, Mike Austin and his group. And Mike was our first speaker last week, if you recall, for our webinar series. So we're going to take, like I said, it's 3 videos. The first one provides an overview of Diversified Tooling Group. The second video kind of drills down a little bit into its group of companies, which includes Midland Design, where they're designing and simulating hot stamping dies. And then we'll take a look at American Tooling Center, which is another one of their companies, and where they have a low volume production hot stamping cell. So I'm going to turn it over to John Basso from Diversified Tooling Group for the first of our 3 videos. Hope you enjoy.
I'm John J. Basso. I'm the owner of Diversified Tooling Group. This is a engineering and manufacturing facility in the state of Michigan for the transportation and the defense industry. We welcome you to our presentation today We appreciate your time. Thank you. Diversified Tooling Group was founded in 1973 by my father, John Basso. He started a very small 5,000 square foot tooling shop, and he had 3 people working for him. So we have very humble beginnings with this company. In 1975, I graduated from college, came on board, and now he had 4 people on the shop floor. And that was the very beginning of Diversified Tooling Group. In 1988, my father bought Best Pro Pattern, and we became a pattern operation also. And in 1992, I bought the American Tooling Center in Grass Lake. In the year 2000, we bought Midland Design, and in 2016, we bought ATC Lansing facility. So at this point in time, we have 3 major tooling operations, and we are a very strong full-service tool and die operation. We also have defense as a second leg to our company, and we are now a major full-service tool and die transportation company. We have currently 425 employees and 775,000 square feet of facilities, and a very strong management team and a very dedicated, loyal, skilled workforce that's been with us for many years. And with that is why we have survived 46 years. We are a full-service tool and die and engineering and manufacturing solutions company. You are now currently looking at a collage of the different product lines that we produce at Diversified Tooling Group at our 4 affiliated companies. Midland Design offers CAD draw developments, FEA simulations, and die processes at the very beginning of the upfront engineering for tooling. Best Pro Pattern designs and builds styrofoam and wood patterns for the foundries, for the castings that we utilize. Superior CAM supplies prototype parts, prototype assemblies, low volume production, and low volume assemblies for a lot of Class 1 aluminum panels. American Tooling Center provides CNC programming, machining, die assembly, die tryout, die buy-off, quality inspection, and home line support, and good quality full service tool and die, mostly depending on Class 1 exterior material. We have a full array of quality certificates, including an A2, L2 laboratory accreditation, also an ITAR defense accreditation, plus all the quality awards that's required for sheet metal and tooling. Diversified Tooling Group facilities, we have 7 facilities in Madison Heights, Michigan, with a total of 235,000 square feet. This is the home of Midland Design, Best Pro Pattern, and Superior CAM. American Tooling Center, as you see, has 3 different locations: 145,000 square foot tool and die shop, 270,000 square foot Lansing Defense Industry, and 125,000 square foot ATC Jackson facilities. These are all heavily craned, heavy electrical, heavy industrial type of facilities. We pride ourselves in 25 years experience with low volume production, stampings, and assemblies. And here's a few of our doors and our roofs and our assemblies that we are providing. Low volume roof assembly is a roof assembly that we have for our customer. This assembly is producing 44,000 roof assemblies. All stampings and all assembly is in-house. This is a right and left hand door that we are supplying at 12,000 of each per year. We have other assemblies that we do have in our facilities. Our press capacity, we currently have 49 major presses. One of these presses is an APT hot stamping production press, but there are 3 tandem lines that we have for running parts within our company. The next slide shows an APT production hot stamping press. This is a state-of-the-art production hot stamping facility. We have our own accredited laboratory for making sure that our hot stamping parts are certified. We have a PHS Metallurgical Laboratory, which is A2LA certified. We're doing R&D work for many of our OEM customers, plus we're certifying our hot stamping parts that they are Martincetic. This is a very good quality laboratory with the right individuals running the laboratory. This shows our APT hot stamping press. And also we have our Prima Next 5-axis laser. Plus you see the water chilling system that chills and cools the water that is cooling the hot stamping dies. We have a 6-step press hardening simulation process at Midland Design. This is a simulation of a thinning of a hot stamping part. This is a quenching plan view of a hot stamping part that we use for simulation for our design of our dies. The quenching simulation represents the cooling of the water lines within the die. Once we establish this simulation, then we proceed with the die design of the hot stamping part. This is an example of press hardened die design, and this is a 6-out with 4 different type of parts. So there's some complexity that we can add into these hot stamping dies. This represents the DTG PHS production tooling. These are hard die production tools with cooling lines for long-term production. The next is the low volume production of hot stampings and assemblies. This represents us running low volume production of hot stamping parts. This press has the ability to run 400,000 hot stamping parts annually. The next component of American Tooling Center is our defense in Lansing. This facility is a very large and well-equipped facility for defense equipment. In this defense industry, we have several people that are highly skilled in welding for NAVSE type of welding, fabrication, CNC machining, assembly, paint castings, and non-destructive testing. And this gives you an idea. We also have for our customers a foundry tooling is Bestro pattern. We have computer-aided pattern design, CNC machining of wood and styrofoam patterns, and we offer that to all the foundries in North America. This is an example of the type of large CNC milling that we provided our company. Some of these components are helicopter blade tooling. There's a large rear axle housing, large CNC machining of water pump housings. We did supply the patterns and the castings and the machining on these components. On the next slide, there's fabrications and assemblies for the defense industry. There's a variety of large, small components that we do supply to our defense customers. We also in-house processing of fabrications, welding, blasting, painting, and assembly, all in-house in Lansing. We also supply these components for the defense industry. To give you an example of the different type of products lines that we have. This is a large base frame that we're providing for the defense industry, and you can see the large scale of this. We're providing one of these platforms every 3 weeks. We also have an extensive metrology department at all our locations. That includes Leica laser trackers, Ferro arm trackers, the Brown and Sharp CMM machines. We have Taurus CMM machines. We also have 4 ATOS cloud scanners. 2 are white and 2 are blue. So we have a very detailed and in-depth inspection equipment that we provide. Thank you for your time today to watch our presentation. Hopefully you learned a little bit more about Diversified Tooling Group. Please visit our website and we will look forward to talking to you in the future. Thank you.
Including a closer look at American Tooling Center, and then again following this, we'll get a look at the virtual. We'll get a look at the hot stamping cell actually in operation. So next up are some of the plant managers. We kick off with Frank Delkov, who's the plant manager of Superior CAM.
Hi, I'm Frank Delkov. I'm plant manager at Superior CAM, and we specialize in prototype and low volume stamping and assembly for the automotive and Class 8 industries. So today we're going to be taking a virtual tour and highlighting some of the areas of that expertise. This is a 3-piece air stretch draw die. The material that this tool is made out of is Kirksite, and it's a zinc alloy that we normally use for prototype applications along with some low volume applications. This material has the ability to be recycled, so at the end of a program, this tooling material will get sent back to the foundry and used again. In Press 9, we've got a low volume production 3-piece air stretch draw die. Now this particular tool has a higher volume requirement. We're running 12,000 units per year on this application, so we built this tool out of a G3500 high ductile cast iron material with better abrasion and wear resistance. In Press 16, we have a secondary form die. Now in this particular instance, we have a 36-inch body side outer panel that has a cam form operation being done to finish form the part. So we form the first stage panel, the draw panel, do a laser trim, and then we run it through this cam form die. This is a Kirksite material. It's a lower volume project. There's 3,000 units per year required. The geometry of the part is pretty soft, which is a plus if you're using Kirksite. And we're using a production intent cam form process. On the Prima Next 2130, right now we're using this 5-axis laser machine to trim door outer stampings. We're burning 2 at a time, 2 right hands on one side of the table and 2 left hands on the other side of the table. This machine is taking the place of what would normally be very expensive trim and pierce tooling if we were running a die complete process. By using the laser, it makes us more competitive by not having to build the more expensive tooling for lower volumes such as this. This is a 12,000 unit per year application where building the expensive trim and pierce tools would take us out of the running for work like this. This operation is making a full door assembly. We do right hand and left hand assemblies in this operation. Manually resistance spot welding the sub-assemblies and then finishing them by joining them with a robotic roll hem process. This is a full aluminum roof assembly that we build here in this fully automated robotic cell. It's a 2-piece aluminum construction, and what's kind of unique about this, there is no resistance spot welding or riveting joining the 2 parts together. This roof assembly is bonded with a 2-part epoxy adhesive and a 1-part anti-flutter, and then roll hemmed into finished position. The volumes on these, we do 4 different styles, and it's around 35,000 units annually that we supply on this product. This is a view of our Kirksite tooling storage yard. We currently have nearly 4 million pounds of Kirksite in our inventory. That was a quick look at Superior Cam's operations, highlighting some of the specialties that we do here. If you have any questions in regard to anything you saw today, please feel free to reach out to us on our website, diversifiedtoolinggroup.com, and we'd be happy to get you any more information you might require. Thank you.
Welcome to Midland Design. My name is Jim Curtin. I'm the Vice President of Manufacturing and Engineering for the Diversified Tooling Group. Here at Midland Design, we have a strong collective of CAE engineers and CAD die designers providing our customers with exemplary support to meet their needs.
Yes, what we had before was this bead. We would point at it, this bead was going straight across, so we decided.
Cold stamp simulations. We are experts in the field for aluminum Class A panels, solving product issues affecting formability, surface quality, or addressing fit or function issues. We utilize AutoForm, PAMstamp, and LS-DYNA software, depending on customer requirements or finite analysis needs.
This is our latest run on the simulation for this.
All right, well, we all know that, as you can see here, we've got these hot areas that we need to improve. PHS press hardened simulations. We primarily utilize PAMstamp software. Our primary goal of PHS simulations is to evaluate quenching rates and make tooling or die recipe corrections to ensure rapid, uniform cooling to produce dimensionally correct martensitic parts.
All right, guys, today we got to look at to make sure that our issue has been resolved in this interference on this cam here. So we're going to look at the simulation to make sure that there's no collisions.
Can you zoom in on the stop?
CAD die design. We have 20 experienced designers that provide both prototype and production tooling solid model designs in both NX and CATIA, utilizing customer standards and deliverables. Midland can provide the full 3D process to initiate die designs or work to a customer provided layout. All right, let's take a look at the hot stamping tool. Understand that the turbulence issue is resolved in the cooling channel. Okay, looking in at PHS CAD die design. We have 5 PHS tool designers with extensive experience in developing specialized tools to meet difficult product geometry needs. Our designers can provide both simple cooled prototype tools and fully conventional production tools to meet any volume requirement, large or small. We're a customer responsive organization, always striving to provide solid solutions to meet their manufacturing needs. Thank you for joining us.
Hi, I'm Todd Hayden. I'm Pattern Manager for Best Pro Pattern. Welcome to our shop. We are capable of making large foam patterns, lost foam die patterns, as well as extractable foundry patterns. We can make wood patterns. We can also make composite checking fixtures. Here's one of our mills machining a gray board checking fixture for checking one of the panels that comes from our prototype division. Here we're cutting a small foam pattern, but we're capable of machining much larger patterns than this. We are capable of taking a print and turning it into a design and then creating patterns from that, fully CNC capable. Thank you for visiting. If you have any further questions, please visit our website.
Welcome to American Tooling Center. My name is John Michael Basso, and I'm the plant manager of American Tooling Center. Today we're going to take you on a virtual tour of the facilities, and I hope you enjoy it. ATC is located in Grass Lake, Michigan. It was founded in 1992 and has grown into a 145,000 square foot tool and die shop. At ATC, we have 3 main product lines that we provide to our customers. Large fabrications, stamping dies for large body panels, hot stamping dies, and low volume production stampings. Our fabrication department is comprised of both this area where you're seeing now, but also the 125,000 square feet location in Jackson, where we have water jets, paint, and additional welding capabilities. All of our weld fabricators meet NAVSEAF certs, and they produce these large fabrications with a turnaround time of 18 days. ATC welds multiple materials, including stainless steel spools. Part of the tooling aspect of our business is that we produce these tools, whether if it's overseas or domestic builds. So as we go through our tour today, we're going to highlight our domestic build capabilities and walk you through the shop. It first starts in the CAD room, where we have NC programmers that provide cutter path NC programming from our simulation surfacing that's provided by a sister company, Midland Design. We also provide reverse engineering and scan post-processing of the scans that we produce on the floor. Once the programming is completed, the castings are then positioned onto the CNC mills. At that point, we have 15 CNC mills. All of these mills have smart software to allow the machinist to program on the floor as the tools are being cut. We can highlight two CNC mills. The first one is the Mitsubishi. This is a 5-axis mill that has a cutting envelope of 6 meter by 3 meter by 2.2 meter and is able to provide fine finish cuts for Class A stamping dies. Additionally, we have two YCMs, one pictured here, that was cutting a Kirksite draw die for our sister company, Superior Cam. Once the dies are machined, they travel to the die shop. In die construction bay, our die makers begin assembling the cold and hot stamping dies in this area with precise accuracy. This is where we dry run the tools, set clearances, and validate trim steels to ensure that the tool is sound and statics are complete. ATC's had an apprenticeship program that started in 1993 and continues today with 7 apprentices. Once the tool has been fully assembled in the die shop and has been bought off, it then travels to the tryout bay, where we have 14 total presses, 5 of them 180 by 96 inch presses with a 2,000 ton lead press. Once the tools are opened up, they begin to barber and stone all working surfaces of the tool. This is especially important to have a fine finish when dealing with Class A outer part tooling. The dies are then loaded into the press and validate and work spot and bearing on the draw and nesting through the line to ensure that the tools can produce a quality part. ATC also runs low volume production. Some of these tools we build our own and run the production for our customers. Once the tools are to a finished state, quality and inspection is implemented. It is a critical part of ATC where we validate dimensional part quality on our CMM or ATOS cloud scanning equipment. With Class A outer tooling, ATC is required to buy off not only the tooling but the part surface. And in the light room, we validate and are trained in how to find defects in the surface of the part and to ensure that we implement those changes in the tools to provide a good surface quality panel. For hot stamping dies, once they've been assembled and completed in the die shop, they travel into our hot stamping laser bay where we provide prototype tooling and parts and production tooling and parts. We utilize our APT production press cell for tryout and low volume stampings. This press cell has 2 7-shelf furnaces. They're all individually controlled and has Siemens controls that allows us to be able to capture data points throughout the process as the part travels from the front of line into the furnace, into the die, and out the back of the line. Our Prima laser and NTC support the blank development and laser cutting of holes and trim of our hot stamping parts. They are both 5-axis and are capable of cutting at fast speeds. For hot stamping parts, quality inspection is a key part, because not only do the parts have to be dimensionally correct and the dies have to be sound, there is an additional metallurgical requirement that we have to include in the processing of these tools. In doing so, we have an A2LA accredited lab that follows CQI-9 heat treating processes and is independent from our company. This provides testing of materials for material suppliers, OEMs, universities, for the advancement of heat treating processes, and we're able to provide that service with our lab, our APT press, and our Prima Laser Next to provide them a good product. Over the years, ATC has taken pride in our people, equipment, and capabilities to provide production tooling, fabrications, and parts on time.
All right, excellent. And so now we're going to turn it over to Mike Austin, who is going to give us an up-close look at the AT&T hot stamping cell that they're using at American Tooling Center for low-volume production. So I'll turn it over to Mike and his presentation, and then Mike's available for Q&A after this last video. So stick around if you've got some questions for Mike.
Hi, welcome to American Tooling Center. We're going to give you a hot stamp demonstration today. This will show you how we perform production at American Tooling Center of various types of parts, mainly for the automotive industry. Here you'll see our AP&T hot stamp press cell. It was installed 5 years ago when we decided to enter the hot stamping business. We've been running production on this vehicle for 5 years, and it's a regular production job for us. We also run a number of other low volume production jobs. We don't do medium or high volume production at our facility. We specialize in the low volume area. The furnace you are seeing today has 7 chambers, and each chamber is individually controlled for temperature and for time to assure that we austenitize the material properly prior to forming. We then take the blanks from the furnace at exactly the right time, and automatically load them into the press, and we control that time within 1/10 of a second. In this case, we have 6 small blanks being loaded and formed in 1 stroke of the press. Those parts are removed. 2 of the parts are cut in half, so we get 8 parts per stroke and essentially 2 car sets per stroke, making the process very efficient. You'll see with the furnaces that we have 7 shelves. We progressively load those shelves 1 at a time. The parts are heated for 4, 5, 6 minutes or whatever is required to reach the proper temperature. The automation removes the parts from the furnace at exactly the right time and takes it to the press and automatically loads it. That process takes about 10 seconds. During that time, reflectors help trap the heat in the blanks so that we lose as little heat as possible. Our target temperature is normally 750 C temperature when the die closes. That allows the part to be made properly, and so that it doesn't get below a certain temperature before it's fully formed. When the press is closed, you'll see that it stays closed for a period of time. That is to quench the material to turn it from austenite to martensite. The hot stamping process is technically called press hardened steel, and what it does is it forms and heat treats the steel all in one step. Following quenching, the parts are unloaded from the rear of the press and placed onto a cooling conveyor. That allows the parts to cool off and stabilize before they're manually loaded into racks. Subsequent processing on the parts is done by 5-axis laser, in this case using a Prima Laser Next 5-axis laser center, that cuts the perimeter of the parts and puts holes in the parts. The Prima Laser Next has extreme accuracy that's required to make parts that have precision of less than 1 millimeter. So we can generally put in the same type of tolerance into a part that with laser processing that we would otherwise have to accomplish with cold stamping. The tooling that we use in hot stamping is water cooled to remove the heat from the die that is put into the die from the part while it is quenching. The tool has to be cold enough when we quench the part to remove all of the heat at a certain rate, generally 50 C per second. However, that heats up the die and we have to use the water to remove the heat before we load the next cycle. So water cooling is a critical part of the die. It determines the cycle rate, and if the water cooling is not uniform, we don't get even quenching of the part and we can get distortion. Tool maintenance is an important issue for hot stampers. It's important to ensure that the finishes are not worn and eroded from abrasion or from tooling pickup of the aluminum silicate. Regular inspection of the tools, cleaning of the water channels, scanning or measuring the surfaces, and refurbishment of those surfaces is often required. Because only one step is required, the tooling cost for hot stamping is less than a cold stamping process. The process runs a little bit slower than a cold stamping process, but is still competitive economically. Parts that are made with hot stamping are the strongest parts used in the automotive industry. Almost all safety cages in vehicles today use hot stamp A pillars, B pillars, roof rails, windshield headers, and other structural components in order to build a safety cage around the occupants of the vehicle. The heat treating process used in hot stamping requires documentation of the process parameters to know that you properly heat treated it. So you'll see a machine making hot stamp parts in today's tour, but in the background there's data collection that is capturing all the information that tells us whether we made a good part or not. And we have traceability on our parts so that if we have a defective part, we can trace it back to the exact process that was used to make that part and take corrective action. When we went into the hot stamping process, we understood that we had to become metallurgists because we were doing heat treating. So we sent our people to metallurgy school to learn all about it. We trained them on how to use our laboratory equipment to measure our process and to establish process windows for proper production. We have our own lab here on site, and we have a certified laboratory by A2LA, which means that we sell our lab results to other manufacturers, other tool makers, and also to research labs and OEMs, materials producers. It's a well-known lab in the industry that's dedicated to hot stamping. Thank you for your attention today and for virtually touring American Tooling Center.
Excellent. Well, thank you, Mike, and to the whole team at Diversified Tooling Group for your efforts in putting together a great tour. So we do have a little time left for Q&A. If anybody has questions for Mike on anything that you saw in those 3 videos. Mike, are you with us over there?
Yes.
All right. Well, thanks, Mike, again for your efforts on behalf of all of our attendees. A couple questions for you, and if anybody else wants to ask a question, go ahead and use that question panel on the control screen there. Mike, you've got the AP&T cell. What are your thoughts on using a conventional hydraulic press for hot stamping, with or without, robotic tending?
Well, it's possible to do that. The main problem with conventional hydraulic presses are they're too slow to form the part quick enough to avoid the part hardening before it gets fully formed.
Okay.
The other problem with that is if you are doing manual handling, you're not controllable and you're not consistent. You need automated handling in order to control the process.
Okay. Mike, you showed us a pretty detailed list of process parameters that you're tracking and reporting. Talk about how you're measuring blank and part temperature throughout the process, I guess during setup and during production.
Well, we use temperature monitoring primarily through thermographs and thermocouples and some contact probes when we're doing setups. And then we also use the infrared parameters that are mounted to the press and the furnace. During production, those parameters are the primary method for measuring the temperature. Some production lines also use line scanners so that you can get a map of the temperature on a part. And most production lines use thermographs, and some are now using machine vision.
Okay. And so, should your monitoring identify, I guess, improper heating of the blanks or lack of heating to the proper temperature or time ranges, what happens to those blanks then?
Well, if for some reason the blanks get past the monitoring equipment and they aren't heated up properly, you're going to find that they weren't fully austenitized, and you're going to get soft spots in the parts, and those parts are going to fail or could fail in service. So it's really important to, in addition to having good temperature measurement and process control of the system, you also need to inspect the parts in your lab, do hardness checks, micro hardness checks, micrographic checks, VDA 238 bend tests. It's something that you have to do to control the parts. So if the parts aren't heated enough, that's the problem. You really need to have a process control over heat treating.
Gotcha. What is the range of sizes of parts that you can make in that press from hot stamp steel? Smallest part and biggest part you can make?
Well, the parts you saw in the video are generally below the typical size that we like to run, but it's possible to make very small parts. And the way that's typically done is you put parts together and then cut them apart with a laser. So you could make small brackets and things of that nature, but you would likely be making them 4, 5, 10 at a time, 20 at a time.
Sure.
We quoted some jobs that are 80 parts per stroke. The largest part is kind of determined by the press size and the furnace size. In our particular case, that's roughly our press size is 2.2 meter by 3 meter. It's a 12,000 kilonewton press, roughly 1,200 metric tons. So we can easily make, 4 B pillars at a time. That's kind of the gold standard for hot stamping. You can make some very large parts as well, as you saw some in the photos. So the largest part we've made was some can trails that run basically from the bottom of a windshield all the way back to the rear door of the vehicle.
Mm-hmm. Okay. All right, good, Mike. I don't think we have any other questions for you. What we got one last one here. For production, the speed in which you can cool down the die dictates the run rate, right? It's all about how quickly you can get the heat out.
Correct. Yeah, the process of loading and unloading the press is relatively constant. The variable is the quench time. So a lot of work is done if you're trying to run at high production rates to minimize your quench time and make it as fast as possible. You have to run at a high enough rate that you turn from austenite to martensite without getting retained bainite. And that phase transformation rate is generally 27 C a second, but most people use 50 C per second of temperature drop in order to guarantee that. Other than that, it's really a commercial issue. So on some of the parts that you saw today, the cooling in the tools isn't that fast because we're doing very low volume production and we don't need to cool it quickly between cycle, and we can run long cycle rates. Mm-hmm. So it kind of depends on the making sure that you quench it properly to get your martensite, and then do you need to do additional quenching rate improvements in order to get better productivity.
Very good, very good. All right, Mike. Well, thank you again to you and your team for putting those presentations together for us, giving us a close-up look at the process. We really appreciate it. So that concludes our webinar session for today, which is the final in the series. I want to thank everyone for attending, and certainly want to thank our sponsors again, Shea, Fagor, and TJ Snow. And remind everyone that all of these sessions were recorded. We'll have an archive of the entire program up on our website very soon, within the next day or two, and we'll send an email out to you giving you a link on how you can access those recorded presentations. And then you'll be able to review what you learned today and last week, and then share the information with others within your organization. So without further ado, I want to again thank Mike and his team, all of our speakers, and our sponsors. Everyone can close their browsers now, and I wish you a good afternoon.